Hey everybody, can you hear me? Raise your hand in the back if you can hear me okay. Yay, all right, great. We have a full house, but I think there may be some seats left. Raise your hand if you're sitting next to an empty seat. Raise it high. There's one. There's one. Okay, somebody come sit. So here's the bad news. Good news, bad news. This course is wildly oversubscribed, which is great because it's a good topic, but bad because you can't all get in. What we did is we convinced the campus to let us over-enroll this course. The rules are you can only have 10% more people enrolled than seats in the room. We got them to blow that away, so we admitted another, 30 people, I think. So we're up to like 340 or 350 people admitted to the class, and there's 297 seats in this room. And the only way I convinced the campus to do this is if if I agreed, like I signed a form that said, I will kick out people who do not have a seat because otherwise the fire marshal will shut us down. And the part of that deal is that the class will be webcasted. So until such time as I bore you guys enough that like 60 of you don't show up to class, it's going to be kind of first come, first served. So that said, I am going to have to ask those of you who do not have a seat to get up and go away and have a Coke or something on your way out though. Before you leave, on your way. Oh, also, if you're not enrolled, if you're auditing, please give up your seat to someone who's enrolled. Final point, before you leave, if you are enrolled and you're taking the class, homework is being passed out today. It is due Thursday. That's in 2 days. To do that homework, you need a piece of paper from the folks, the TAs at the door to get a course account. So please, on your way out, pick up a course account, and then information on the homework will be on Piazza. Lectures should be online shortly. My apologies. All right.
I'm sorry?
Please. All right, everybody, let's get going. So I apologize once again, but we should try to jump in. All right. Thank you all for being early and eager and pushing your way into the room and getting seats. That's great. All right. So for those of you who are watching on TV, we love you too. Let's get started. So today, any class that you take, the professor really should answer these questions at some point. Why take this class? What the heck? What will we be learning about? I forget even what who's about, but like who are we, I think is what that was about. How's the class going to work logistically? And then, for instance, I'll give you just a little bit of a taste of the kinds of things we're going to be learning about this semester. A little flavor, just enough to get you in trouble with your homework. And that's going to be lecture for today. So it's going to be rather light today. The rest of the semester obviously will be more technical. But today we're going to be kind of on the light side. Okay, why? Why take this class? Well, first of all, a little note of history. The first lecture delivered in this room was this class, and it was me, and that was 3 years ago, which is kind of cool. So I love this room. And 3 years ago, I could feel this happening, and now it has happened. But when I started teaching database at Berkeley in the mid-'90s, I'm pretty old, there was nothing interesting about this topic. I'd be like, data, it's really cool. There's all this really interesting computer science. And students would be like, hey, can we go program video games and figure out what that web thing's all about? We're not really interested in data. We want to do some computing. We want to compute on some stuff. And 3 years ago when I taught in this room for the first time, it was pretty clear to me, and in fact, if you look at the slides from 3 years ago, it says 5 years from now, data is going to be huge and you're all going to be employed working on data. We're well into that. So I don't think I need to convince you so much that data is going to be at the center of many things In fact, frankly, data is pretty much at the center of everything. It's almost hard to think about our world now without thinking about the ways in which we can quantify it and then take advantage of that quantification. There is a mobile mic if you want to come on up. All right, can you guys keep it down, please? Thanks. All right. So, things like Moneyball, if you saw the movie or read the book, obviously data made the Oakland A's great. This was an interesting issue of Wired some years ago. Wired's kind of over the top, but still they called it the end of science. And what they said was, the quest for knowledge used to begin with grand theories. Now it begins with massive amounts of data. Welcome to the petabyte age, which already kind of ages it, right? It's like petabyte, kind of big, not that big. I don't know. So that's like 4 years ago. And then The Economist, which is, really mainstream media, started talking about this data deluge and big data in the early 20-teens, okay? And by now, this is like everybody gets it. You can talk to your grandma about big data, and she sort of at least has heard of it. So this is a thing. We all know it's a thing. Some numbers. I tried to get up-to-date numbers, but actually the best numbers I could get on like how much data is there in the world were from this IDC study a few years back, 2011. So at that point, they were saying doubling every 2 years, 1.8 zettabytes were going to be created in 2011. And to give you a sense of that, infographics were really cool in 2011. 1.8 zettabytes would be like every person in the United States tweeting 3 tweets per minute. So that's 4,320 tweets per day per person for 26,976 years. It's kind of silly, but it's a way to get your hand around it. Or, 200 billion HD movies is kind of the equivalent of how much data was going to be generated in 2011. Okay? And if you stacked it up in 32 gigabyte Apple iPads, it would build a mountain that was 25 times higher than Mount Fuji. So that's pretty cool. So there's a lot of data, and that gives you kind of a feel for it. This is only growing, all right? So, yeah, credit where credit is due. Here's the most that they published this year, not as much entertainment, but we're up to 4.4 zettabytes in 2013, and they're predicting getting up to 44 zettabytes in 2020. So there's going to be a whole lot of data. Now they're stacking up tablets to 2/3 of the way to the moon. I don't know how they figure out how to do these things, but what's the best analogy? But whatever. It's a lot of data, okay? There's a lot of data out there. So what the heck is going on? Where's all this data coming from? Well, from the internet, I guess. Okay, but really what do we mean? So, if I set all the people in the world typing at keyboards as fast as they can, we wouldn't generate that much data. Like Twitter actually isn't that much data. Okay, so you get everybody typing really fast. There's 4 billion people. It's just not going to generate that many bytes. All right, some, okay, decent amounts, but not that much. There's other stuff going on. One thing that's going on is there's lots of copies of the same stuff, basically movies. And when you measure internet bandwidth usage, it's for sure just, a small number of things being sent too many times to different people, right? So that's all about staging that data out and caching it and putting it in different places to reduce bandwidth usage. But storage-wise, a lot of the world's magnetic storage is being taken up with like copies of movies. Okay, so that's some of it, and that's actually not that interesting at some level, at least not today. It's not that much unique data. We don't do that much with it, but that's part of it. Okay, but what's really kind of interesting is what I call the industrial revolution of data. This is happening under our feet, where basically data is being stamped out by machines. Data used to be crafted by people typing at keyboards, or people making movies or making music, creating content. Okay, but now data is increasingly being generated by machines. Primarily these days, software logs, right? So all our software is spitting out logs about what's happening with it. That software is in the center of many of the systems of the world, commerce and government and so on. And so that just generates a lot of data about human activity. And then there's like physical stuff. So RFID tags started happening. That's how you get into Soda Hall with your swipey card. GPS started happening. And we started talking about the Internet of Things, which is something people at Berkeley were working on like 15 years ago at least. We called it sensor networks. But it's really happening out there now more and more. Quantified self is a piece of that. People are starting to measure their own bodies. And then high bandwidth stuff like microphones and cameras are just generating lots of data based on what's going on in the physical world. So this data is being stamped out and formatted by machines. It's not like Shakespeare writing down and generating all this data. All right, and that changes the kind of data we have, and it changes the coverage of things that we have data about. All right, and it changes what we can do with that data. And so, today's probably the only day we'll take the luxury of asking some of these questions. But, you might ask the question, how does this make you feel if everything gets measured and stored and indexed and machine learned and predicted? Well, I don't know. Let me give you some food for thought on that front, okay? So some years ago, so there's this, right? Start with this. Information is knowledge. So, this is good. Clearly, mankind has always wanted more information. This is a good thing. Albert Einstein said that, actually. So that's pretty cool. Knowledge, obviously, is power. Sir Francis Bacon said that. So this is good. And then, of course, as you know, with great power comes great responsibility, which was said by Spider-Man's Uncle Ben, right? So I think, there's a subtext to this whole class, and there's a political science class, I think, right before us, right? There's a subtext to this whole class about what we as engineers are enabling and what technology is going to bring us that I think, merits at least a little discussion on the first day of class. Okay, so some years ago, back in the mid-2000s, I was working with a startup in the city, and they were hosting public data on the internet and auto-generating charts and creating sort of blog-style discussions about the data. And one of the statisticians at the Organization for Economic Cooperation and Development, which is a European multinational organization, he got really excited about this. And this is what he said about the idea of having data online. This is like deep in the Bush era, by the way. So a little political context. With a collaborative spirit, with a collaborative platform where people can upload data, explore data, compare solutions, discuss the results, build consensus, we can engage passionate people, local communities, media, and this will raise incredibly the amount of people who can understand what is going on. And this would have fantastic outcomes, the engagement of people, especially new generations. It would increase knowledge, unlock statistics, improve transparency and accountability of public policies, change culture, increase numeracy, and in the end, improve democracy and welfare. Awesome. Okay. So certainly you can do lots of good stuff with data. And I think increasingly one of the other things, he's a statistician, so not surprising, one of the other things he's hinting at is that the ability for large numbers of people to reason about data is kind of key to a good society of the 21st century. Okay, so I think for all of us as engineers, computer scientists, potentially educators, mentors of people as you grow, I think there's a lot of hope and positivity that you can engage in the ability to get data. And so you look at people who are trying to do like sunlighting public data or trying to organize data.gov or things like that. There's a lot of public good that can be done by just basically increasing transparency of what's going on in the world through data and tools around data. Okay, so definitely some big positives. And I put that first because there's lots of negatives, right? They're coming. Right? But there is a lot of positive to be done here. And I think you got to keep your eye on that and hopefully help with it. So Stephen Colbert has this awesome word of the day thing. I don't know if he still does this anymore. But some years back, he got all excited about Wikipedia. Did anybody see these? He had Jimmy Wales on Colbert. It was awesome. So he defined this word called wikiality, like reality, but it's wikiality. And he said, together we can all create a reality that we can all agree on. The reality we just agreed on. And so to illustrate this, he went into Wikipedia and he edited the topic on elephants to say that there was an overabundance of elephants in Africa and that people should start hunting them. And then he said, Colbert Nation, you have to keep this page up because people could just change it back. And so TV watchers were continually updating the elephant page to say there were too many elephants in Africa. So this created kind of a thing. And then Jimmy Wales, who's the founder of Wikipedia, came on the show, and that was interesting. Jimmy Wales, so Colbert asked Jimmy Wales, I hear you have Wikipedia in lots of different languages. And Jimmy Wales said, yeah, we have Spanish and this and that. And Colbert says, shouldn't that Spanish Wikipedia be in English? And Jimmy Wales said, oh, and man, now we're going to have to shut down the entire Spanish Wikipedia and lock it down because you're going to change it. So, definitions will welcome us as liberators. So what does it mean when you let anybody update the official, knowledge of the world? It's kind of fascinating. It's maybe not that fascinating to us. When Wikipedia was just happening, it was a little more interesting. But still, there's some crazy stuff on Wikipedia. And it gets actually kind of interesting when you try to scrape data out of Wikipedia. Not just the text, but the data in the info boxes. So here's one I ran across in a conference talk. So this was a conference talk on a knowledge base that's being built in Germany called Yago, which is used in a lot of AI projects. And they're scraping Wikipedia to get data about people, places, and things and use that as a knowledge base for doing various machine learning tasks around mostly natural language processing. So to try to extract people and places and other sort of common constructs out of text. And they had this example about John Coltrane, who's a famous saxophonist and composer, right? And they had the Wikipedia box of all of his categories that he fit in. And when you go on Wikipedia and you look for stuff, they have these info boxes on the right, and it says all sorts of stuff that I knew about John Coltrane, avant-garde jazz, and you could argue, right? Say that genre doesn't make sense. He was not a hard bop guy. He was more of a, I don't know what, right? It's more of a modal guy or something. But you could argue about that, but that's not what's interesting, although it's up for debate. What's interesting is this. He is a 20th century Christian saint, all right? Which is kind of weird, although you may happen to know that in San Francisco there's the Church of John Coltrane where you can take your saxophone and go and worship, actually. And in fact, he was granted sainthood by a small African-American church, which now it says has about 5,000 members. Okay, so there's at least 5,000 people who think he's a Christian saint. But when you use it as like a table in a database or a knowledge base, and you start looking up, 20th century saints, John Coltrane just gets tossed in the bucket with Mother Teresa and everybody else, and most people would be a little surprised, maybe even John Coltrane. All right, so weird stuff happens when we all get to say what the data is. And maybe it's good, and maybe it's not. All right, how does this make you feel? How much data does the NSA look at daily? This might make you feel great, by the way. It makes me feel, I don't know how it makes me feel. The NSA looks at 1.6% of total internet traffic, which is about 29 petabytes a day. So this is traffic on the wire, traffic in motion, in fairness. But they're capturing it, all right? So for context, Google in 2010 said it had indexed 0.004% of the data on the net. So by inference from the percentages, the daily NSA data collection is 400 Googles. Holy, wow. I don't know if that's true, frankly. But it's daunting, all right? Or 126 Facebooks a day being gathered by the NSA. Okay, so I don't know how that makes you feel. It's interesting. There's certainly some really cool big data challenges to work on at the NSA, no doubt. All right. Here's another one. I had a graduate student who got really interested in data research having to do with healthcare in Africa. And he spent a lot of time in Tanzania and Uganda, and one of the things that motivated his work was this statistic. 76% of children born in sub-Saharan Africa are unregistered. Not only do they don't worry about there being too much data. They don't worry about people spying on them. They don't even know who's been born and maybe would need to get a shot one day when they're passing out the shots. In a lot of these countries, there's no data, zero zip. Right? They'd love to have data because then they could help people with it. Okay. Interesting thing. So this student, Kwang Chen, who's started a company after graduate school here in Berkeley called Captricity, now in Oakland, he went down there, and this was the kind of data they had at the healthcare clinics he visited in Tanzania. One of the doctors who really could realize that sort of statistics could help them figure out a little bit about how to deliver healthcare at this clinic, would put these things on the wall, hand-drawn charts. Okay? And this is like a database by the standards of that village. Okay? So data in that context, and Kwang went ahead and worked with these people and got them sort of using cell phones to take pictures of data and upload it to the cloud where it could be processed in the big city. All kinds of good stuff happened from that research. And they've done a whole bunch of disease and AIDS studies using that technology. It's pretty cool. And this company started as well. But data there, there's just not nearly enough of it. Not nearly enough. Right? And a lot of it has to do with sensing and data gathering. So how do you get data in these contexts? And a lot of times the answer is paper, because people will write stuff down on paper. It's a great technology. It goes everywhere. All right, so that's interesting. There's, of course, the classic pie chart percentage that looks like Pac-Man and the percentage that doesn't. So that's data that makes you just feel silly. If you actually want to generate that chart, you have to come up with some numbers. Anyway. So anyway, data will certainly be at the center of major issues and events in our lives. I think it's worthwhile as we think about stuff in this class to think about what we're enabling and keep this stuff in mind. And as you think about your next job and so on, just what are they using the data at your company for? Or at your nonprofit organization or your university or whatever you happen to work at. All right, so that's a little bit of the why for this class. It is big stuff. It's really big stuff. It's society-changing stuff. Okay, so what are we going to learn about? Well, what is a database? All right. Pretty easy to see the database in this thing. It's an IBM data processing system. It has a label on it. So back in the day, databases were pretty easy to identify. They were also really, really boring, and they weren't even considered really worthy of academic study. This was mostly work that was being done at places like IBM. back in the 50s and 60s, although they actually ended up doing a lot of really interesting computer science. Most people would agree that your bank has a database that holds your money, and the classic example of transaction processing is banking, so that's not terribly surprising. So this is a website on the census. You probably would believe that the census is a database, and the data behind this website is a database. That's not terribly surprising either. All right, so is Google a database? How many people think Google is a database? How many people think Google is not a database? All right. Fair enough. How many people, I don't know. Most people didn't vote. I won't ask why. All right. LinkedIn, so there's I think there's a lot of databases here, but let's look at some. Say happy work anniversary to your friends who have a work anniversary. That's pretty much look up your friends whose work day equals today. So that's pretty clearly just a database query. That's pretty boring. Okay, what about this? Pulse recommends this news for you. Well, I don't know. News is kind of text. I don't know if that's a database or not. Maybe that's a database. And then recommendations, is that databases? I don't know. Maybe, yeah, probably. I don't know. People you may know. This one's pretty interesting. There's a graph, a social graph here, and wandering around that graph and recommending who you may know. That's an interesting special kind of database, maybe. And then I get ads for Hadoop because that's the kind of geeky guy I am. So the ads they choose to target to me is probably coming from some database. There's a lot of databases floating around on this one web page. Right? And actually, most services you use, Facebook, LinkedIn, and so on, issue hundreds of requests to dozens of databases before they pull you back a page. Okay. Oh yeah, and then I have all sorts of communications that have been stored in various ways. Maybe that's a database too, depending on how you define it. All right, this is a terminal from my laptop. This is varsys log. Is that a database? How many people think that's a database? How many people think that's not a database? All right, yeah. It's a really crappy database. I can, by the way, tell you the history of why system logs look like that. It's all based on Berkeley, and it's kind of sad. But as a guy whose company helps people clean up these logs, though, I'm kind of happy about it. But it's really pretty bad engineering. It's messy. All right, and then these guys, are they databases? I don't know. Your phone's got some database software on it. Probably so does your Fitbit. They're generating data. They're storing data. They're communicating data. I don't know. GoPro. So GoPro, is not only taking pictures, but there's all sorts of information it's getting about how you use the device, right? So it's not just the primary function of these devices, but also sort of where you go in space and when you use it and all kinds of things that they can gather, right? If you always wear your GoPro on your motorcycle helmet, then they know where you go. Right? So I don't know. Is it a database? Maybe. So you know what? Let's not split hairs. Let's just say a database is a large collection of structured data. So why don't we rule out like prose? Right, except that our homework, I'm going to make you look at a whole lot of prose, and so it's kind of going to be a database project. But there's structure really everywhere, is the bottom line. Anything you look at, you can extract structure from and do analysis on. So pretty much any data could be database data. And then the question is only really whether you're organizing it or not. But these days, most of the time, you organize it kind of when you need it. So you decide you're going to take all the works of Shakespeare and do something with them. Well, once you carve it up and get the statistics out of how Shakespeare used different words, you have a database. Okay, so pretty much any collection of data is a potential database these days. Now, a separate question is what's a database management system? What's the software, okay, that supports your database? And well, it's a chunk of software that stores, manages, and/or facilitates access to data, to databases. Okay, so we're going to be pretty Catholic with the small c, meaning open-minded, about what we call a database. I'm not going to get all hung up on it. That said, and actually what we're going to learn in this class should be useful across all these different kinds of uses of what I might mean by database. That said, I don't want you to go out in the world talking differently than everybody else. So when you go out in the world, most people, when they talked about databases, up till reasonably recently, we're talking about relational databases with transactions, a la Oracle, Microsoft SQL Server, IBM DB2, and the like. All right? So that is a common usage. It's also a really mature technology with a lot of interesting stuff in it, so we'll make reference to it a fair bit in this class. Your textbook is very focused on relational databases. The lectures you'll see based on the order of material and the way we kind of break it apart are less focused on the relational database per se. So today, the market and the terms are actually in rapid transition. So the tech behind the relational database and the tech behind the databases that are being built at places like Facebook and LinkedIn and Google aren't so different, really. So the techniques you're going to learn in this class, many of which were invented like in the 1970s, 1980s, 1990s, a lot of that technology is the technology that people are either using or reinventing in large-scale big data systems. All right. But there are various pressures to kind of remix this technology, to revise it, to put it together in different ways, and to change some of the key assumptions. And those pressures are coming from a bunch of directions. All right. We're going to hopefully at least touch on a little bit of this in class. But because things are changing very rapidly right now, and we are in kind of a time of transition, I will ground you in sort of the more textbook stuff, which will give you the tools and abilities to invent the next generation of stuff, frankly. Okay. But hardware is changing quite a lot. So when your textbook was written, all large databases of note were working on magnetic spinning disks. All right, and that is just not true today. There's lots of data that's being either staged or permanently stored either in RAM or on flash, which doesn't have quite the same performance characteristics as magnetic disks. So after 50-odd years of building systems focused on magnetic disk, there's a lot of rethinking going on. Okay, the basic ideas are the same, but suddenly you're like, oh, hey, I don't have to worry about disk seeks, and I want to make sure that I don't have memory contention because everything's faster. So hardware, as always is true in systems, in computer systems, hardware is changing some of the rules. Data volume is changing some of the rules as well, and it actually works against the hardware point. You can get a phenomenal amount of data in your laptop in memory, especially if you compress the data. You can run a pretty big compressed database. A lot of the analyses you could ever want to do, you could do on your laptop. On the flip side, you walk into a place like Facebook, and they'll tell you they're running Hadoop on, I don't know, like 5,000 machines for this, and 100 machines for that, and 20,000 machines for this. And you sort of can't do the arithmetic. It sort of almost doesn't pan out. And they're storing it on magnetic drives to a large degree. All right, so when you're dealing with things at very big volume, some people, some companies, some engineers, will sacrifice efficiency for scalability and ease of management and ease of writing software. They'll say, you know what, disk drives are fine. We're going to spread this out on lots and lots of machines. We're not going to worry about optimizing each individual machine. Okay? But because we're at this huge scale, we're also going to give up on some of the things that we wanted in relational databases, because to make something work on tens of thousands of machines or to work across the globe, we have a speed of light communication between machines. You can't implement some of the classic algorithms in an efficient fashion because they assumed you could access memory like super fast. Okay. So there's been a lot of work in the last 15 years on relaxing the constraints of traditional databases, giving up on some of what they promised. And then in the last about 5 years, trying to get some of them back again, because it wasn't such a good idea to throw out the baby with the bathwater on that stuff. So that's an interesting space right now. It's dealing with data at just gigantic volume. And then, last but not least, because data is now clearly at the center of computing, it's hard to imagine what a computer's for if it doesn't have at least a decent amount of data, right? Like, it used to be computers were for computing, right? Like calculations and stuff. Well, it's not really true anymore. Computers mostly revolve around the data that they store and access. And so with that, basically, all the things you might want to do with computers are things you want to do on large amounts of data. So there's a very wide variety of usage of how people use big data now. Machine learning algorithms, graph processing, a whole bunch of workloads that really didn't exist even 10 years ago at the level of the database. And now they need to be pushed down to storage for efficiency. So that widening variety of usage is opening up a whole bunch of challenges as well. So these are all changes. And frankly, like, this is the first lecture of a research class in databases would be to start talking about those three things. I want to flag them today so that when, 3 weeks from now, and we're talking about spinning disks and disk arms and disk seeks, and maybe we're assuming we're on a single node, you won't be like, Hellerstein, man, you're living in the past. Like, I'm not living in the past. It's good for you to learn how this stuff works on some of the technology, which is the traditional technology, but be aware that when you guys go out in the field, the tools and techniques we're going to cobble together in this class are going to have to be rethought to some degree as you apply them in other contexts. And I'll try to flag that as we go, okay? But the stuff you'll learn is useful today, it's useful tomorrow, and it gives you the basis for what will be happening in 5-10 years. All right, so it's a really good time, bottom line, to focus on the fundamentals. I will not teach you the internals of exactly how Oracle works, because it kind of doesn't matter. But I will teach you the building blocks that allow you to build systems like Oracle or Hadoop or a NoSQL database or whatever comes next. Right? All right. So what is a database really? Or database management system, I should say. Is an operating system a database management system? So this is a classic no, okay? And for many years, the OS and database communities distinguished themselves based on this, sort of the software engineering communities and the research communities. Clearly, you can put data in RAM, so that maybe is a database. Every programming language does this, really. So maybe Python is a database system. Probably not. It's fast. RAM is great. It's super fast. It's random access, so you can look at any part of RAM you want. And that sounds awesome, right? So what's wrong with that? But it gets better. Every operating system comes with a file system, right? It manages these things called files on a disk, usually a persistent disk, like a flash drive or a magnetic disk. It allows you to do things like open files and read files and jump around in them with seeks and then close the files, right? And it lets you set protection on the files. This file's unreadable. This file's only readable by me, et cetera. So that's kind of like a database. What are some drawbacks of a file system relative to RAM? Why don't we just put all of your Python state in the file system? What's the point of RAM? Yeah. All right, disk drives are still pretty slow. Even flash drives are pretty slow, actually. They're like at least an order of magnitude, probably multiples of order of magnitude slower than RAM access, depending on various configuration issues. And I neglected to put into this slide deck, there's analogies of like, this is how long it takes to get to memory, this is how long it takes to get to disk. It's sort of like things that are in this room versus things that are somewhere on campus. You know, it's that kind of thing. It's like an order of magnitude or more time to get things that are on disk. So it's slow. Anything else about file systems that maybe isn't so good relative to RAM? Yeah. They're not really random access. You can seek to an offset in a file, but if it's on a magnetic disk, you have to kind of spin the disk and move the disk arm, and it makes that horrible chunkity noise, right, to move around. And it doesn't have memory cells the way that RAM does, and you don't have a language layer on top of it that lets you follow pointers around quite as nicely. So it's not really a random access device. RAM is random access. Yeah. Oh, interesting. So what I heard you say was it might be getting used by other programs. So the API to the file system is shared across multiple processes in an operating system. And if you remember from your operating system class, one of the first things they do is virtual memory, which prevents multiple processes from accessing RAM, right, at the same time. So there's something in the file system that might worry you with multiple processes going on. Now, multi-threaded programs have the same problem in RAM, okay? So concurrency, which is another word for this, is a problem that actually comes up in multi-threaded RAM-based programming as well, but it came up earlier historically in places like file systems and databases. So that's an excellent point. Okay. So here's a thought experiment related to that, actually. You and your project partner are working on homework 1, which will be passed out today. All right? Let's say you were doing it on the Inst machines, which you're not, which is good, but supposing you were, and you were both running VI or your favorite editor on the same file, and you both save at the same time. Okay? So we're going to do a little poll. You both saved your changes to the file at the same time. Whose changes survive? A, yours. B, your partner's. C, both. D, neither. Or E, question mark. Could I get a vote? How many people raise your hand if you believe A is always the answer? How about B? Is B always the answer? Is C always the answer? D? But E? Yeah, pretty clearly, right? Non-deterministic, what the heck's going to happen, including things like the file is destroyed, all kinds of crazy things could happen. It's very, very bad. File systems do not like you to do this, and they don't help you with it that much. All right, here's another thought experiment. You're working on your file, and the power goes out. All right, which changes survive? Well, nowadays you have a battery in your laptop, so it's not so bad. But all your changes survive? None? All since the last time you pressed the little picture of a floppy disk at the top of Microsoft Word? You believe they still have that icon? Which changes survive? I don't know. I mean, the floppy disk icon is awesome, right? Because you click on this thing that looks like a storage device from 1988, and then some pixels make it look like you pushed it in as if it were a real button. And then the power goes out. So was it saved? I don't know. What about when the button comes back? Is that better? Like, nobody knows, right? And then, I don't know if you noticed this, but Microsoft has a very sophisticated operating system that they've been working on for like 2-3 decades with a very fancy file system underneath it called NTFS. It's got all kinds of logging and recovery built into it. But what happens when you start up your machine after you crash in the middle of Word? You start up Word again, and what do you see? Recovered file number 1, right? So the guys in the Microsoft Office division have implemented their own recovery algorithms. Why? I guess because the Windows file system guys weren't getting it right? That should make you nervous. Okay? It's weird when the same vendor is doing recovery at the application level and at the system level. It suggests that they're not using shared components that are reliable.
Word is on Apple products and other products as well.
A fair, though I think somewhat flawed point was made in the front here, which is that, well, Word does run on the Mac, and so maybe they're just protecting themselves against Apple's bad operating system. But the truth, if you know anyone who's worked in the Mac division of Microsoft, like that is a forlorn, sad little corner of Microsoft that actually, they don't make decisions based on what's going on in the Mac division. Okay, so here's the thing. You're a developer. Like you're writing Microsoft Word, and you go to the file system guys, you're like, what's going to happen in this scenario? They go, So how do you write code for that? And the answer is you don't. You just have to worry about all the possibilities and code against that. Right? And when you take non-determinism of your compute infrastructure, suppose I told you that some of the bits in your RAM might flip sometimes. Sorry, sunspots or whatever, but it happens once a month, maybe once a week. How about if you're running 1,000 of these machines, it happens every 2 or 3 seconds. How do you write software, right? So you need to have abstractions that are reliable as you go up the stack, okay? And a big thing that we're going to talk about in this class is that a database management system is a piece of software that makes programmers' lives easier because it's going to give us some abstractions that will allow us to stop worrying about some stuff, okay? That's the answer to that question, right? All right. So what more could we want than a file system? We could want these API contracts regarding data. I want to be guaranteed that I don't have to think when I write a program about other people running instances of the program at the same time. I don't want to think about concurrency control at application level. Please handle that for me. I don't want to think about replication of my data in case my media fails. Please handle that for me. Wouldn't it be nice if your family photos had that property? I guess if you put them up on Flickr or Picasa, they do, but until they get there, they don't, right? iPhoto has lost some of my cherished memories. So replication, recovery, things like that. I want guarantees from the API so that I, as a developer, don't re-implement that stuff up at application level. And to that end, it's a lot of data, right? So I want to have a high-level language, sort of a domain-specific language for data. I don't want to be writing my data access in Python because, frankly, Python's not a very nice language for dealing with large amounts of data. I want a simple, efficient, well-defined language that's appropriate to the domain of working with data, something like a query language. And we could talk lots more about that. Some people believe that what I just said is complete horseshit. Some people believe that what I said is horseshit in the other direction, which is that all programming should be done this way, and Python should be thrown out the window for even, writing mail clients. So I don't know. It's an interesting question, what's really a domain-specific language. But certainly there's a long tradition that says that there are good domain-specific languages for querying data. Because there's lots of data, I want a system that will do the standard stuff that you need to do with data, implement it once efficiently and scalably. Be fine if it was a library. It doesn't have to be Oracle, okay? But I don't want to have to rewrite sorting over and over every time I have a terabyte that I need to sort, okay? A little anecdote along these lines. So this is like bread and butter. Everybody knows this. Nobody would implement sort every time they need it for lots and lots of data. But as the machine learning stack was developing at companies like Google, what would happen is they didn't have abstractions yet. They still kind of don't in the machine learning space for what are the core algorithms and system components, library components that you need to build a good machine learning stack. And so what would happen, apparently, is everybody would come to Google back in the early 2000s and write naive Bayes classifiers, because they just got out of college and they knew how to do that. So it was cool. And apparently, if you did a search in the Google code base for naive Bayes classifiers, you get thousands of implementations, right? And it's such an easy algorithm, you can write it in a few lines in the right language. So here in the database domain, we're going to be able to actually bust this down into a very small handful of design patterns and algorithms, which is really quite nice, and they're very widely usable. Okay. And then data modeling is actually an interesting topic, surprisingly interesting topic. These days, I think common wisdom, conventional wisdom, which I agree with, is that most data you're going to get by volume is going to get spooled off of these machines. It's going to come from software logs. It's going to come from devices. It's going to have whatever crazy log format it had when it was born. And that's fine. And you'll dump it somewhere. And then one day you'll want to analyze it. And you'll take that horribly structured data. You'll say, well, what do I need to input into my analysis package to answer the question I want to answer or predict the thing I want to predict? And to do that, what you're going to do is you're going to take the data from one format, structure, or model, and you're going to map it into another format, structure, or model. And you're going to do that custom because you have a new analysis you want to do. But what's going to happen in your company is you're going to start to productionalize that analysis. It's going to eventually turn into like the recommender system for your website. Okay? And as part of that, it's going to kind of mature, and you're going to get some software engineering around that process you went through to go from raw data to cooked data. Okay? And you're going to want to integrate that cooked data with other data, like LinkedIn, for example. They don't just look at what you type in. They also get resume data from third parties, and they get demographic data from the government and so on. And you need to start to be able to put this data together and understand how one thing relates to another. And what you do is you end up evolving a data model. Okay? Now, back in the textbook days, if you read the textbook, the way they say that you build a database is you turn on the database, you define your data model, and you type in all your table names and column names and data types and all this stuff, and then you populate it with data. Right? That's not actually how things work that often anymore, but the basic theme that at some point, for software engineering purposes and for data management purposes, you want to model your data, that remains very, very true. All right? And that's something that a database system should provide, and we'll learn about in this class. Now, there's a persistent, through the ages belief that this is just a simple matter of programming, all these things. You know, why have a system for this? Why have a library for this? Just build this stuff. It's not that hard. And I would say that is true for all of computer science. Okay? There's nothing false about that. It's just, you know, these things are tricky, and there's really no reason to do them over and over. And when you do them over and over, you get weird artifacts, like you get recovery happening in multiple layers of your stack and bad things happen. And this is a persistent lesson that communities relearn. So you heard about the Microsoft example I gave you, but the same stuff happened, for instance, at Amazon, which was basically where the NoSQL database was invented and popularized. What ended up happening is they had this very scalable NoSQL database called Dynamo that they got a lot of attention for. Had a lot of copycats in open source, and it gave very few guarantees on like whether two replicas of the same data item would really be the same. So what ended up happening as they built applications is all the applications had to deal with the fact that you might have divergence of replicas, and that code got pretty hard to manage and pretty expensive to keep live. And so eventually they built a better infrastructure than Dynamo, which actually has more guarantees than the NoSQL stuff that a lot of the copycats now ship. Okay, so organizations have a tendency to start building things from scratch and then to abstract out reusable components and guarantees with APIs. And so you'll learn in this class some nice cut points, some nice libraries and guarantees where traditionally it's been good to layer things. And hopefully that'll save you some pain along the way. Or maybe when you see this pain somewhere, you'll say, you know, I think we could alleviate some of that pain with some shared services. Okay? All right, so the current market, so for the record, Berkeley has since the mid-'70s, had a tradition of impact from our research systems at Berkeley on the industry. And I also have done research at Berkeley that we've transitioned to startups and stuff like that, which is where I've been for the last 3 years. And I think it's good to know what's going on in the software market, both the internet software market, so understanding what's going on at Google and Facebook and LinkedIn and the like, but also the enterprise software market, people who sell software to other people. What does that software look like? One thing to keep in mind on that, and this is really important, I don't know if you get enough of this message here at Berkeley, right near Silicon Valley. There's like 5 companies that have, you know, Twitter and up-sized problems, right? There's Google, there's Facebook, and everything else is smaller. But there's only like 5 to 7 companies that have these really, really big data problems. And they make certain trade-offs that optimize for their scale. Those trade-offs often involve making the software really, really simple, so it scales out really far. Those designs are often very poor designs for almost everybody else on the planet. Okay, so Hadoop, for example, was not really well engineered for anybody but Yahoo, and it's taken 8-9 years for it to be something that you can kind of deploy at a bank now. But just because something's been built to scale up to Google doesn't mean it's a good design for almost everybody else on the planet. And often it doesn't mean it's an interesting design either, because a lot of times they just simplify things to the bare minimum so they can scale it. Okay, so one thing we'll keep in mind as we talk through the semester, you should be raising your hand, or at least thinking in the back of your head, will this scale up to Google-sized things? And if the answer is no, will it scale up to like things that are a tenth the size of Google? Because that's almost everybody, right? So keep these things in mind. As you talk with companies in general, lots of technology is almost more interesting sometimes and certainly more widely beneficial when it's done at a scale that most people can use. Okay? All right. When we talk about the database market, though, the relational database vendors still dominate certainly sales of databases. Not Bytes, because Bytes are in the internet companies, but sales for sure. And they've been around for a long time, very mature technology. All right? And actually, when you peel back the cover of something like Oracle or IBM, they've implemented pretty much every trick you can think of. Like, there's just 30, 40 years of stuff in there. Now, they don't innovate a lot as a result because the software stack's kind of so thick and crufty, you can't, it's not very malleable anymore. But there's a lot of goodness in there. Okay? And in open source, MySQL and PostgreSQL and SQLite and all these things are used very, very widely. And Postgres, which is something we'll play with probably when we do our SQL homeworks, it's actually a very full-featured relational database built here at Berkeley originally. And you can get pretty good databases out in open source. There are variants of the relational database that you'll hear thrown around when you go out in the field, things like main memory databases or in-memory databases, which has come up because memory is getting so big, but you still want that database abstraction layer. And then column-oriented databases where you store things by columns instead of by rows, which doesn't sound like a very big deal and at some level kind of isn't, but you hear about it a lot in the market. These are variants of relational databases. At the same time, the sort of open source of NoSQL is growing very quickly. So on the analytics side, this is things like Hadoop MapReduce from Yahoo, essentially, and the open source community. And then Spark, which comes from Berkeley, has been growing very quickly recently. And then key value stores like Cassandra from Facebook and MongoDB and Couch, which are independent companies. Those are getting widely used as well. We'll talk about those systems in this class. Obviously, search is an important special case of a database. If you're dealing with large text corpora, which is the plural of corpus, which means body, then you obviously need to deal with text search. So you know about Google and Bing. On the open source side, Solr and Lucene share the same history, but those are open source packages that are designed for text database search. Interestingly, databases in the cloud are expanding very quickly. So Amazon EC2 has a bunch of services for data management. Elastic MapReduce, which is a Hadoop deployment, Elasticsearch, which is a Solr deployment, and then Redshift, which is basically Postgres, which is a relational database thing that you could use in the cloud, is their fastest growing product ever, actually, at EC2. So lots of people using databases in the cloud. You wouldn't think people would put their corporate data up at Amazon, but a lot of people are. And Microsoft has its own stuff, and there's smaller players as well, like Heroku, where you can go get a database and put things in the cloud. And a lot of those are built on relational database or other technologies like that. Okay. So we're about 50 minutes into this thing. So what are we going to learn about in this class? All right. Well, first of all, these design patterns for computing with data. My feeling always has been like a database is not, it doesn't have a purpose in and of to itself. Database systems don't have purposes in and of to themselves. I should be teaching you things that you can use to build interesting computing systems. Right? And that's what this is going to be about. You're going to be learning design patterns for computing with large amounts of data. All right? And if in your career you need to build a system that deals with large amounts of data, you will probably go back to some material from this class. Okay? So that's primarily what I want you to walk away with. Also things about like structure and data. When, why, and how should you structure data? In that process of going from raw data to a particular analytics output to a data product like a recommender system or a corporate database. Like when and how do you deploy sort of data modeling ideas along the way? I do want you to get the basics of like how does a relational database like Oracle work? How does a search engine like Google work? At least at a kind of nuts and bolts level, if not with all the refinements, because God knows there's a million refinements on both of these. You'll learn SQL. It's very useful. Everybody uses SQL still. You will learn about NoSQL systems and what they do, which is actually really easy, but we'll cover that along the way. You'll learn how to manage concurrency, and the techniques that were developed in the database community for managing concurrency and transactions have been applied all over computing, including to hardware. Okay, so this is a very basic topic. It's not really a database topic. It's a topic about how do you think about concurrent processing, which is a thing that computers just do, especially when you have more than one of them. Okay, we'll learn about fault tolerance and recovery. We'll learn some very particular specific techniques for fault tolerance and recovery, and we'll talk a little bit about alternatives as well. And then we'll talk, I'm going to try to weave this in from day one. We'll talk about scale out. How do you parallelize things by getting them on multiple machines instead of just one, and kind of farming out compute into clusters. And we'll also talk about replication to some degree when we talk about NoSQL. And then there's if you go to my personal webpage and dig around, there's a poem by Herman Melville, the guy who wrote Moby Dick, on art. The poem's called Art. And there's this line in it that I really like, where he's like, he's talking about what is art and how do you make art, but he talks about there being audacity and reverence, that combination of like being willing to just be out there and say that things are wrong and just reinvent stuff, and at the same time, the reverence, the idea that there are things that you should respect and admire and learn from. So we're going to try to do both of that. I'm going to try to encourage both of that in this class. There's a lot of classical material in the database field that's worth knowing, and it's also probably good to think about what would happen if you threw it out the window. Okay? So we're going to try to ride that balance as we go through the semester to some degree. Okay, so summing up this part of the lecture, data is, as we said, it's kind of at the center of everything. In particular, though, before I go on, I really feel like data is at the center of computer science. And since that is the major a lot of you guys are in, I just want to take a minute and really think about how computer science has changed, even in the last 5 years, but certainly in the last 20, from a field where data was sort of a add-on afterthought to a field where data is kind of at the core. Okay, so we're going to talk about this in a couple different ways. But fundamentally, you might think in this class we're going to learn to apply computer science to big data. It's actually the other way around. We're going to learn about stuff in this class that's going to allow you to do computer science. All right, because computer science going forward is going to be about large volumes of data. It already is today, frankly. Okay, so this class should really apply very broadly. All right, and before I go on, just a little more rah-rah, and then we'll get into some of the details. This is a slight adaptation of what I said 3 years ago. This was the stuff where I said, in 5 years. I left it on the slide, actually. I should have changed it. So 3 years ago, I said in 5 years, those professions would become very big professions. So we're 3 out of 5 years into it. People who program cloud systems, yeah, that's a big thing. Right? A lot of the jobs you might be looking at coming out of this school will be building systems that scale up to Amazon, Google, Microsoft, Azure, or Facebook type of sizes. Data scientist was people weren't even willing to say that it was a term 3 years ago, and now it's very clearly a growing field. We have a data science class at Berkeley. There's a data science major at Berkeley in the iSchool, and there's lots of people hiring data scientists. Okay, data engineer is kind of one that still hasn't caught on as a word, but lots of people who work in IT around data systems are essentially engineering pipelines to build data. A lot of those cloud programming tasks are data engineering tasks. Machine learning architect, what does it look like to build a stack for machine learning? These are things that are emerging today. Not just what's a clever algorithm for better clustering, for example, like you might learn in a machine learning course, but how do you build a pipeline so that you can build, say, a recommender system or a fraud detection system? And what do the pieces of that pipeline look like? The engineering side of machine learning is really just emerging. But I said 3 years ago, in 5 years, it would be a large fraction of the computing workforce, and I still think that you guys have a chance to be leaders in this space, because it's not too late. This is still emerging. So now is definitely the time to jump into these data-centric pieces of the field. Okay. A little administration. So who are we? So briefly, I want to introduce 4 out of the 5 TAs. And I'm Joe Hellerstein. So just background, I joined Berkeley in 1995 out of graduate school. I've been here since. I've had various meanderings through industry. I ran a research lab for Intel. I've been involved in a couple startups, including one that's still ongoing, mostly in the database and internet kind of area. What else can I tell you? I went to Berkeley for a year, so I'm a Berkeley alum, so that's good. That's probably it. And then I'll let these guys introduce themselves. You want to go first? And actually, I'll give you the microphone just real quickly.
Hi. I'm Derek Leung. I'm a third-year computer science and math major here at Berkeley.
Good.
Hi, guys. My name is Vikram. This is my last year at Berkeley. I taught 186 last spring, and yeah.
Hey, I'm Michelle, and this is my last year at Berkeley as well.
I'm Jay, and I'm a third year.
And I'm Anthony, and this is my last year at Berkeley as well.
All right. All these guys have taken CS 186. and Vikram has taught it, and they're going to be very close to home with you guys because they're very recent experience with the class. So I have always actually enjoyed working with undergrad TAs more than grad TAs, and I'm real happy to have these guys aboard. So it's going to be good. The other thing I'll say is when the class gets bigger, we're able to have more TAs. More TAs means a better structured course, quite frankly. So in some ways, it's good to have this many people. All right, so let's get into the nuts and bolts of the class. Workload. There's going to be homework. We're going to try to keep a real-world focus to the homework. So we're going to do things like wrangle up some messy data to extract structure from it. All right. In fact, that's the homework's going out today. I better hurry to teach you how to do it. We're going to code up some scalable algorithms. So I'm going to have you implement an interesting analytics algorithm in a language that can scale up and be parallel, probably SQL. We're going to modify the internals of a big data engine, namely Spark, which is the one that's being built here at Berkeley. So you're going to get your hands inside sort of a hot new system and modify it to add function to it. And then towards the end of the semester, we'll work with data visualization technologies to build applications on top of the database that provide data visualization. So those are all things that are very useful things to know out in the real world, and we'll exercise ideas from class. In order to just kind of keep things ticking along, we're going to have what we call vitamins, which is the weekly quiz. It's good for you. You should take it. I used to not do this before I had lots of TAs. So when I taught here 3 years ago, we started doing this. Before that, we didn't have quizzes because there were only 100 students. There were 2 TAs. It was like, who's got time to write all these quizzes and grade them? The thing was, I used to get teaching ratings and say, good class and all that, but like, the midterm would come, and like there'd be all this stuff that wasn't in the homeworks, and we just like hit us like a truck. We had no idea we were supposed to actually learn that stuff from lecture. So it's like, that's bad. So this is going to just kind of keep it ticking along, make sure you're paying attention and remembering what happened in class. They're not going to be hard. They're going to require you to keep up, okay? And they're really there for your health, like a vitamin. All right, and they will count towards your grade a little bit because if you're like me or like I was in college, nobody really wants to do extra work. You got too much going on. So we have to give a little incentive for you to do them. So it will affect your grade. I would expect that anybody who's diligent will get perfect scores or near perfect scores on these quizzes through the semester. Okay, they're not going to be trick quizzes. There'll be 2 midterms. The dates have not been fixed yet because we have to get an overflow room to be able to administer the midterm to all the other people. So I have to get that set up. But the midterms, there'll be 2 midterms and a final, of course. The final date and time is posted on the web. We have a website. You can get to it at cs196berkeley.net. The office hours sections, all that kind of stuff are up on the website. Everything should be linked from the website. There is a textbook. It's Database Management Systems 3rd edition, which is getting a little crusty by now, but there is going to be no 4th edition because both those guys work at Microsoft. Okay. They used to work at Wisconsin and Cornell, and now they work at Microsoft. It's a sad thing. So you guys should go get PhDs and take their jobs. Write a really good textbook. It's an okay textbook. It's pretty good. But like I say, we're going to have to augment it with some updates for modern times. And we're going to jump around in it a fair bit because I don't like the very traditional sort of organization of it. It's not the right way to think about this stuff. It's very relational database centric, and it really starts thinking about data modeling way too early. I would not buy any of the alternative textbooks, but you might want to look at them at the library sometime if you don't like the way that Ramakrishnan and Gerke explain something and you're confused. A lot of times just reading the way someone else explains it helps a lot. So I've recommended one secondary textbook, which is the Silberschatz and other people, Korth and Silberschatz textbook. It's pretty good, too. It's the one I used in college a long time ago. And it's fine, but I wouldn't buy it. These things cost way too much, which is why no one wants to write one anymore, because you don't make any money and no one likes you. And it's a bad deal. The website has links to programming resources, things like, learning Python and SQL and stuff like that. Just, you could Google them yourself, but we've provided some handy links. Grading and hand-in policies, all that are on the webpage. I want to take a minute to talk about cheating. Don't cheat. My God, you're at Berkeley. This is one of the, perhaps the greatest institution of learning in the world. You're here to learn. You'll be fine. You'll be fine. You don't need to cheat. It's crazy, okay? And beyond that, you're cheating yourself, which is really true. And we'll catch you, which is also true a lot of times. So, we have software that will crawl over your software, and, we have eyes in the sky and big data and all that. So don't cheat. Okay. And if you know someone's cheating and you really want to tell me, you can, but we don't have an honor code like that at Berkeley, I don't think. All right, Piazza, really important. All class communication via Piazza. There's like 350, 400 of you right now. I don't want to get email from you guys. That's too many people, okay? I also don't want like 25 of you to come up to me before class. I can't talk to 25 people when I'm setting up the microphone. I'm sorry. If it was a class with 20, we would totally do it. It'd be very personal. But we got 350, 400 people. So we should use Piazza, post questions. The good thing about that is when you ask a question, the answer is probably relevant to like 30 other people anyway, right? So ask the question out loud on Piazza. We'll answer it in a timely fashion. That is definitely the way to get hold of us. Same applies to your TAs, although since they're dealing with you in batches of like 35, usually 70 actually each, they might be able to take a little email, but still, it's like not fair. 70 people emailing them at once is a disaster area, right? So read Piazza regularly. You are responsible to know what's going on there on a more or less daily basis. That's it. There will be homeworks. The homeworks will be either solo or in teams of 2. If you will have to stick with your team of 2 through the semester, so please, do your speed dating this week because next Tuesday we will pass out our first 2-person homework assignment. Question? So right now, discussion sections, we're going to try this week. You can go to any discussion section you like. All right, a lot of them are double. They're 2 at the same time. Sometimes there's one in like Wheeler and one in Echeverry. So you might, if you like want more attention, I would walk over to Wheeler, just because like a lot of people would be too lazy to do so. We're going to try that this week. If we get too much skew, some sections are too big and others are too small, just by happenstance, then maybe we'll randomly allocate you guys. But for now, we're going to just say go to whatever section you want, and we'll see if that works. Okay? Good? All right. We're going to have to take a little time to learn some computer science now. So here's the thing. 2 homeworks are being passed out now, right now. First one is homework 0. It's worth 0 points, which is cool, but if you don't do it, you get kicked out of the class, which is bad. Okay? So this is just to make sure you register with GitHub and you get a course account and all that stuff so that we can deal with homework 1. If you don't have sort of like the wherewithal and the moxie to sign up for GitHub and fill out your course account and log into your instructional account in the next 2 days, well, then you probably don't want to take the class, right? And there's 100 other guys out in the hallway who do. So please do this by Thursday or the consequences, we will probably boot you from the class. Okay? It's going to take almost none of your time. Do it. You have 2 days. It's 48 whole hours. I know you don't sleep anyway. Go for it. Homework 1 is due in a week. Homework 1 is a real homework. It's not hard, but it is kind of, takes some time. I did it over the weekend. It took me some hours. So, it'll take you some more hours. But it's not hard. In fact, it's so not hard that there's almost no instructions other than how to set it up because you're basically just going to figure out how to do it yourself. But in the next 15 minutes, I will teach you what you need to know to do homework 1. And details on the GitHub repos and all that stuff are accessible from the course website. The interesting information, like the how-tos for homework 0 and homework 1, are both on GitHub. You can read them on the web first if you don't know how to use Git, and they'll step you through all the details. Okay, so a little for instance. Let's learn a little computer science, just a little bit at a high level, enough to kind of get you dirty with your homework. This is what's called a von Neumann machine. How many of you guys saw the new Alan Turing movie? It was okay. It was a little boring. It was okay. I would go see it. It's like history and stuff. Anyway, the von Neumann was another math guy. He was Hungarian, though. He wasn't British. And he came to the States, and bad things didn't happen to him, which is good. And he defined the kind of architecture that we've built for our computers. It's called the von Neumann architecture. And all our computers and programming languages basically use this abstraction for how a computer works. You have a CPU. That CPU has stored instructions in it. Those instructions are executed by a program counter in order. Like 1, read something. 2, do something. 3, write something. 4, go to 1. Like that's a program, okay? And then there's a memory bank where you can do the little reads and writes, and you can put little numbers in that memory bank, okay? That's a von Neumann computer, all right? It's different from a Turing machine abstractly, okay, but this is the model of computing we use. And when you think about Python or Java or Scala or almost any language you would use today, it's kind of like that. There's kind of this linear order of instructions, and there are these things you can put values in and take values out of, and you can kind of go to in one way or another with function calls and recursion, right? They're still von Neumann computers, single-threaded, if you like, until you decide you want 2 of them. Okay, and then you have 2 threads, but they're 2 von Neumann machines, right? You're still thinking von Neumann, okay? Oh, and then, by the way, there's data. Boing! Where does that go? I don't know. They didn't have data back when von Neumann was doing computers, all right? They really barely had storage. and it's not part of the computational model. It's over on the side. There's some special command that can like push things out of the memory bank into the database. All right? That's what Unix is too. That's what every programming language you're likely to work with, except maybe SQL is. Well, maybe not MapReduce either, but most programming languages are like, this is terrible, all right? Because this is not the way the world is. The world is the database and like a whole lot of computers. It's not one little single computer with one ordered list of instructions, right? But this is crazy. It's deep in your brain. When somebody asks you what's an algorithm, and they're not a computer scientist, they're like an English major, like an algorithm is kind of like a recipe, you know? Like when you're going to bake a cake. It's like, you know, you crack an egg, and then you mix it, and then you add flour, and then you mix it some more, and then you add sugar. Like, that's nice. That's how you bake a cake. But that is not how you, like, create the Hostess company, which creates delicious cakes for mankind, right? Like, we're doing things at scale here, right? And so it's crazy that we still think this way. And in your lifetime, the way we talk about algorithms, I believe, will also change substantially. We will not be talking in this sequential manner. We can't be talking in this sequential manner 20 years from now. But when we're dealing with big data, we can't talk this way today. Okay? All right, we scaled up. We got lots of those things now. We still got this big database on the side. That's how Hadoop works, okay, just for the record. There's like all these processing nodes, and then there's the Hadoop file system, which is like some other software abstraction. It's what Google built. All right? Why? Because they didn't have time to think about anything else. They were building Google. It was like 2004. But shame on the Hadoop community for doing exactly what they did and still doing it today. Right? We're all crazy that Google doesn't do that anymore. They do all sorts of other things. But that's kind of the idea. Is like you take a big storage abstraction and you stick it in front of your big compute abstraction, which is nuts. Really, the way it looks is that. And that's the computer you're supposed to program. Right? It's a bunch of components which have storage, and they have memory, and they have the ability to do processing, and you want to program them en masse, the same way that like a commercial bakery is going to make sure to produce lots of cakes all en masse. Okay? There might be some recipes deep down inside it, right, that get executed sequentially somewhere, but you need to orchestrate all that. That's the hard part. So this is really the key to distributed computing and parallelism, is dealing with lots of data that's been spread around on lots of computers. All right, so today, in the last 15 minutes, we're going to learn some basic patterns for dealing with big data that will scale in this fashion, and that will work also for data on a single node that doesn't fit in memory, right? Because everything you do that doesn't fit in memory, you might as well do on two computers. Basically, everything I'm going to teach you now, you can just do it on multiple computers at the same time, instead of kind of doing it a little bit at a time in one computer, and I'll show you what that looks like. So the two basic patterns you're going to use in your homework and in a lot of things in this class are streaming computation model and divide and conquer, basically. Okay, one form or another. So here's what I mean. First, simplifying assumption. I'm taking away your arrays and your lists and all those data structures that you always like that have order in them. All right? And I'm giving you back collection types that do not have order, like sets and relations and collections of records. Okay? So there's no order anymore intrinsic in your data structure, which means that there's no order intrinsic in your program. Okay? So you can do things in any order you want, which is totally the opposite of von Neumann with its first do this, then do this, then do that. Okay? So things can happen in any order you like. Unordered handling of unordered data. This will set you free. This is really good. And all scalable systems embrace this, essentially. So disorder is a friend of scaling. When you can order things to your liking, you can do things like reorder stuff for cache locality. You can reorder things to make sure that two items that need to show up at the same time do, even though maybe they're going to arrive at different times from different places. So you can postpone some stuff. You can work on things in arbitrary batch sizes. So if your memory on this machine is smallish, but your memory on this machine is biggish, you can do smallish amounts of work here and biggish amounts of work there. So you can pick your batch sizes to fit that. Also remember, memory is a hierarchy. You got your L1 cache, your L2 cache, your RAM, your flash, your disk. And you may want to move data in and among those levels of the memory hierarchy. And you'd like to do it in a way that's efficient, which means that you want control over the batch size. And you can do that if we don't care what order you do things in. It's okay, for instance, if some data comes at you, you're like, later for you, I'm going to put you over there for now. I'll get back to you later. That's fine, because it doesn't matter that you handle things in order. Okay? And most importantly, if the ordering doesn't matter to the semantics of your program, then you can tolerate non-determinism in ordering, i.e. parallelism. So if this machine races faster than this machine, that's fine. They're working on different items. These items get handled first, no big deal, because we didn't care what order they got handled in anyway. So the key to parallelism without coordination is the ability to have disorder in your program and tolerate non-determinism of ordering. Okay, so this is going to be a great thing. I'm taking away your lists and your arrays and giving you sets. All right. Here's the thing, though. Data tends to arrive often in streams. It may not come in any particular order, but it often comes, at least at one node, in an order. And what we want to do is we want to take all that data, and it might be big. It might be a petabyte of data or a terabyte of data, and maybe all you have is your laptop. All right, let's say you have 100 gigabytes of data, and you want to stream it through your MacBook, okay, and work on it. Well, here's a simple case. All you want to do is for every item that's in that collection of data, you want to apply a function to it, f. Right? This is like the map operation from MapReduce, okay? So the goal is to compute f of x for every record and write the results out to another big disk drive. All right? And the challenge is to do this in a small amount of RAM and to not call that read-write interface too often, because every time you invoke read or write, the operating system does all kinds of crazy things and devices get involved and it takes time. All right? So you want to amortize, so it means get the most out of or take a lot of activities and pay for them only once. Amortize the cost of those reads and those writes. So here's a basic pattern for streaming. It's the simplest thing ever, but you'd be surprised how often people don't do this. So the naive thing you'd do is you'd say, well, oh my gosh, I've got this file. I'm going to have to work on it. So the first thing I'll do is I'll bring it into memory, and then I'll iterate over the items in the file. And it's like, well, that's not going to work, all right? Because the minute you try to bring that file into memory, you're dead. But that's what you do when you open a file in your editor, right? You're like, oh, cool, I got a new data file. I'm going to look at it in Sublime Text. You like open it up, and it goes, right? Because it's loading the whole damn thing into memory, which is insanity. So we're not going to do that. We're going to stream. We're never going to have the whole thing resident in memory at the same time. But we'd like to use memory efficiently to amortize reads and writes. So watch this. The approach is we're going to read a sizable chunk, whatever seems to be appropriate to amortize those reads and writes, into an input buffer in memory. So we'll read some stuff. We'll copy it into this input buffer. And then we'll start picking things in RAM. So this box is RAM. We'll start picking things one at a time out of the input buffer, applying f of x to them, and putting them back in RAM in an output buffer. Okay? And then there's two rules to keep in mind. When the output buffer is all filled up, it's going to be a fixed size. When we fill it up with stuff, the minute you put something in it and it says, oh, I'm full now, then write it to the end of a file, and then erase with the buffer. Right? The other rule is when the input buffer's got nothing in it, get some more stuff. All right? A buffer load. And that's all. And the one thing to keep in mind is that based on f of x, those things may not be synchronous. So for example, imagine that f is compress. So you get big objects in, little objects out. So you might read 100 big objects. Each one of them gets compressed by 10. You fit 1,000 compressed objects here before you have to write it out. So you will do 10 reads before you do a write. Right? And that's okay. That's fine. Similarly, if it's decompressed, you'll do 10 writes before you do a read, and that's fine too. So these aren't in lockstep. The streaming is not in lockstep. These buffers allow you to have different rates for reading and writing because your function may make things bigger or smaller. Very simple, okay? But this is like the most basic pattern for dealing with a big file in a small amount of memory, and it's at the core of a ton of tricks. And there's lots of interesting algorithmic issues about what can you compute this way exactly, what can you compute this way only approximately. There's all kinds of work on streaming models of computation. But the basic system architecture of it is just that, this little design pattern, and you're going to need this for your homework. Unix pipes do this. Oh yeah, you want to parallelize this? Well, that's no problem. Remember, this is one machine in our rack of machines. It's got an input disk and an output disk and a memory. Oh, our rack has more machines in it with more data. That's cool. They just do the same thing. So this parallelizes forever, right? It's just like every one of these machines does its thing all by itself, and then you're done. Okay, so this parallelizes trivially. Now, if you had an ordered data structure and you said, well, all the items across all the disks have to be processed in order, because I wrote a sequential program to do it, this wouldn't work, right? This is all because we don't care about the order in which these things are done. Okay, Unix pipes do the same thing. So these streams are basic to Unix. And the utilities in Unix, there's a lot of utilities for working with data, and they deal with the buffering in the operating system for you. And you just connect things together with pipes. So you can kind of build queries over files in using Unix utilities and pipes. Here's a query. Find students who got 100 on one assignment and got 0 on no assignments. And you can use a combination of, you said to get the rows out of the grades file, but not the header. And you put it into grep. And then you put it into grep minus v, which throws away things. And then you do a cut to get the right fields out, and you're done. Okay? And this all happens in a pipelined fashion. So that file, grades.csv, could be really, really big. But Unix is going to make sure that it doesn't run each one of those commands on the file in memory. It takes it row by row. In Unix, it takes it text line by text line. That's all you're given, unfortunately, is text line delimiters. But that's what it does, and it streams it through memory. Okay? You're going to want to use this for your homework. Right? But this design pattern of pipes and single I.O. at the front and the back is exactly what we just saw a picture of. A bunch of the Unix utilities you may or may not have heard of are in this format. You probably will want to read the manual pages for some of these for your homework. They're very, very useful, very handy things to know. Not exciting to learn about. Very useful. Here's another thing you need to do all the time. Here's another design pattern for data. And frankly, this is also like a core computational artifact. It's in almost every computing task you need to do, but it's rarely talked about in this fashion. Rendezvous. I need to make sure that two items are in memory at the same time. Okay? This is pretty much what computation is, actually, and I'll save you the philosophical discussion of that. That's for another class. But rendezvous is key to database systems, certainly, because the join algorithm, for example, which is core to databases, is about making tuples that are in one table and tuples that are in another table connect up. And we'll spend time talking about joins a lot. But rendezvous also happens in, say, messaging. I want to make sure that a sender and a receiver find each other in space and time. And I'm going to have to make sure that somehow the sender and the receiver's data is in the same place at the same time in order for that handoff to happen. All right. So streaming was easy. We just did one chunk at a time. Rendezvous algorithms are a little trickier. They need to make sure that two items are co-resonant in memory at the same time so that we can compute on both of them. And they may be coming from different streams. So how will we make sure that they don't miss each other? And if you've ever tried to teach a small child how to catch a baseball or hit a baseball, it's like, oh my God, how do we make sure that the bat and the ball are in the same point in space at the same time so they get hit? Like, try to teach that. It's like incredible that people can do that. We have to do that with data, all right? And we do it all the time in computers, but it's a time-space rendezvous, all right? And there may be many of these that you have to do a computation. So rendezvous is trickier than streaming, and usually we do it with divide and conquer. What we'll do is we'll divide up the data set into things that couldn't possibly rendezvous with the same stuff. All right, so like put all the apples over here and all the oranges over there because we're only going to compare apples to apples and oranges to oranges. All right, so you do tricks like that to divide up the problem. So these are often called out-of-core algorithms because core is a very old word for memory, for RAM. Right, so algorithms that deal with data that's bigger than RAM are often called out-of-core algorithms, and they typically involve more interesting things than streaming. They typically involve some kind of rendezvous orchestration. So the typical way you do this, and this is just the design pattern. We'll see examples of this on Thursday, and you'll implement them next week. But the typical way you do this is you'll allocate a chunk of RAM, let's say B buffers of RAM, B chunks of RAM, capital B. We'll use one of them for reading as a read buffer, just like we did with streaming. Okay? So we'll be able to read things in decent-sized chunks. We'll use one of them for a write buffer, just like we did with streaming. But we're going to have B minus 2 buffers left over to hold on to stuff so that we can do rendezvous. So that something can stay there in memory long enough in time that something else that it's supposed to match with it will show up. Right? So that the bat and the ball will both be in RAM at the same time, essentially, if you like. Or the sender and the receiver will know that there's a place where that message will be that they will both be able to get access to over time. So that's what the B minus 2 chunks are for. And the basic idea here, a typical pattern, not the only pattern, because sometimes it's reversed, but a typical pattern, is you streamwise divide the data into B minus 2 sized megachunks. Okay? So we're going to take the data, we're going to stream it in, and then we're going to take B minus 2 sized megachunks of it, and we're going to write them to disk. So you'll bring in B minus 2 chunks through the input buffer. You'll massage them and do whatever you need to do to them to get them all ready for the future. Maybe you'll sort them. Maybe you'll build an index over them. Maybe you'll, compute a statistical signature of them. I don't know what you're going to do. But you can give them a good massage. Then you're going to write them off to the disk. And then you're going to take B minus 2 more and you're going to massage them and write them off to the disk. And now on the disk you have partitions of your data. And then in the conquer phase, those have all been conquered individually. And then in phase 2, we need a streaming algorithm over those conquered meta chunks. So now that we know things about each of these chunks, we can start bringing chunks together in memory and doing stuff to them. Right? And this streaming is going to ensure some kind of rendezvous. Right? I know this was super vague, but we're going to see exactly this pattern on Thursday. So I wanted to get that out there. And this divide and conquer, you divide the file into partitions and you either conquer them on the way in or you conquer them on that second phase. That's going to be a typical pattern we're going to see over and over. Okay, that parallelizes also, but This is where parallelism gets a little interesting in systems like MapReduce or databases or whatever. The data starts out all partitioned, but it might not be partitioned in the way you like. Okay? It might be partitioned in, and you can't form the mega chunks you want to form. So what you might need to do is repartition the data. So the first thing you might do is send little bits of your data to other machines. So in this picture, those are 3 computers. These are the same 3 computers on the right-hand side, okay? Or maybe they're not, actually. Maybe they're 3 spare computers, but they could be the same 3 computers. And what you're doing is you're repartitioning the data, and then these guys, once it's been repartitioned, can act locally because the things that should go together, all the apples are on the top one, all the oranges are on the middle one, and all the pears are on the bottom one. And that's the first phase, is to partition up the data across machines. All right, I think we got through everything I wanted to get through today. There's a variety of Unix utilities you'll need, but that is about it for today. So I'll see you on Thursday when we were going to talk about out-of-course sorting and hashing. Homework. Oh, wait, stop. Don't go anywhere. Stop right there. In order for you to do homework 0, you need a course account form. The TAs have the course account forms. Don't move. Don't move. They will exit the room first. They will catch you at the door, and rendezvous will happen. All right, so guys, go to the door. Do not leave without a course account form. No, at the door. Let them get to the door. Go to the door. All right.
I'm sorry?
Please. All right, everybody, let's get going. So I apologize once again, but we should try to jump in. All right. Thank you all for being early and eager and pushing your way into the room and getting seats. That's great. All right. So for those of you who are watching on TV, we love you too. Let's get started. So today, any class that you take, the professor really should answer these questions at some point. Why take this class? What the heck? What will we be learning about? I forget even what who's about, but like who are we, I think is what that was about. How's the class going to work logistically? And then, for instance, I'll give you just a little bit of a taste of the kinds of things we're going to be learning about this semester. A little flavor, just enough to get you in trouble with your homework. And that's going to be lecture for today. So it's going to be rather light today. The rest of the semester obviously will be more technical. But today we're going to be kind of on the light side. Okay, why? Why take this class? Well, first of all, a little note of history. The first lecture delivered in this room was this class, and it was me, and that was 3 years ago, which is kind of cool. So I love this room. And 3 years ago, I could feel this happening, and now it has happened. But when I started teaching database at Berkeley in the mid-'90s, I'm pretty old, there was nothing interesting about this topic. I'd be like, data, it's really cool. There's all this really interesting computer science. And students would be like, hey, can we go program video games and figure out what that web thing's all about? We're not really interested in data. We want to do some computing. We want to compute on some stuff. And 3 years ago when I taught in this room for the first time, it was pretty clear to me, and in fact, if you look at the slides from 3 years ago, it says 5 years from now, data is going to be huge and you're all going to be employed working on data. We're well into that. So I don't think I need to convince you so much that data is going to be at the center of many things. In fact, frankly, data is pretty much at the center of everything. It's almost hard to think about our world now without thinking about the ways in which we can quantify it and then take advantage of that quantification. There is a mobile mic if you want to come on up and... All right. Can you guys keep it down, please? Thanks. All right. Things like Moneyball, if you saw the movie or read the book, obviously data made the Oakland A's great. This was an interesting issue of Wired some years ago. Wired's kind of over the top, but still they called it the end of science. And what they said was, the quest for knowledge used to begin with grand theories. Now it begins with massive amounts of data. Welcome to the petabyte age, which already kind of ages it, right? It's like petabyte, kind of big, not that big. I don't know. So that's like 4 years ago. And then The Economist, which is, really mainstream media, started talking about this data deluge and big data in the early 20-teens. Okay, and by now this is like everybody gets it. You can talk to your grandma about big data, and she sort of at least has heard of it. So this is a thing. We all know it's a thing. Some numbers. I tried to get up-to-date numbers, but actually the best numbers I could get on like how much data is there in the world were from this IDC study a few years back, 2011. So at that point, they were saying doubling every 2 years, 1.8 zettabytes were going to be created in 2011. And to give you a sense of that, infographics were really cool in 2011. 1.8 zettabytes would be like every person in the United States tweeting 3 tweets per minute. So that's 4,320 tweets per day per person for 26,976 years. It's kind of silly, but it's a way to get your hand around it. Or, 200 billion HD movies is kind of the equivalent of how much data was going to be generated in 2000 and generates a lot of data about human activity. And then there's like physical stuff. So RFID tags started happening. That's how you get into Soda Hall with your swipey card. GPS started happening, and we started talking about the Internet of Things, which is something people at Berkeley were working on like 15 years ago at least. We called it sensor networks. But it's really happening out there now more and more. Quantified self is a piece of that. People are starting to measure their own bodies. And then high bandwidth stuff like microphones and cameras are just generating lots of data based on what's going on in the physical world. So this data is being stamped out and formatted by machines. It's not like Shakespeare writing down and generating all this data. All right, and that changes the kind of data we have, and it changes the coverage of things that we have data about. All right, and it changes what we can do with that data. And so, today's probably the only day we'll take the luxury of asking some of these questions. But, you might ask the question, how does this make you feel if everything gets measured and stored and indexed and machine learned and predicted? Well, I don't know. Let me give you some food for thought on that front, okay? So some years ago, so there's this, right? Let's start with this. Information is knowledge. So, this is good. Clearly, mankind has always wanted more information. This is a good thing. Albert Einstein said that, actually. So that's pretty cool. Knowledge, obviously, is power. Sir Francis Bacon said that. So this is good. And then, of course, as you know, with great power comes great responsibility, which was said by Spider-Man's Uncle Ben. Right. So I think, there's a subtext to this whole class, and there's a political science class, I think, right before us, right? There's a subtext to this whole class about what we as engineers are enabling and what technology is going to bring us that I think, merits at least a little discussion on the first day of class. Okay. So some years ago, back in the mid-2000s, I was working with a startup in the city, and they were hosting public data on the internet and auto-generating charts and creating sort of blog-style discussions about the data. And one of the statisticians at the Organization for Economic Cooperation and Development, which is a European multinational organization, he got really excited about this. And this. Hey, everybody, can you hear me? Raise your hand in the back if you can hear me, okay? Yay, all right, great. We have a full house, but I think there may be some seats left. Raise your hand if you're sitting next to an empty seat. Raise it high. There's one. There's one. Okay, somebody come sit. So here's the bad news. Good news, bad news. This course is wildly oversubscribed, which is great because it's a good topic, but bad because you can't all get in. What we did is we convinced the campus to let us over-enroll this course. The rules are you can only have 10% more people enrolled than seats in the room. We got them to blow that away. So we admitted another, 30 people, I think. So we're up to like 340 or 350 people admitted to the class, and there's 297 seats in this room. And the only way I convinced the campus to do this is if if I agreed, like I signed a form that said, I will kick out people who do not have a seat because otherwise the fire marshal will shut us down. And the part of that deal is that the class will be webcasted. So until such time as I bore you guys enough that like 60 of you don't show up to class, it's going to be kind of first come, first served. So that said, I am going to have to ask those of you who do not have a seat to get up and go away. And have a Coke or something. On your way out, though, before you leave, on your way. Oh, also, if you're not enrolled, if you're auditing, please give up your seat to someone who's enrolled. Final point, before you leave, if you are enrolled and you're taking the class, homework is being passed out today. It is due Thursday. That's in 2 days. To do that homework, you need a piece of paper from the folks, the TAs at the door, to get a course account. So please, on your way out, pick up a course account, and then information on the homework will be on Piazza. Lectures should be online shortly. My apologies. 11, okay? And if you stacked it up in 32 gigabyte Apple iPads, it would build a mountain that was 25 times higher than Mount Fuji. So that's pretty cool. So there's a lot of data, and that gives you kind of a feel for it. This is only growing, all right? So, yeah, credit where credit is due. Here's the most that they published this year, not as much entertainment, but we're up to 4.4 zettabytes in 2013, and they're predicting getting up to 44 zettabytes in 2020. So there's going to be a whole lot of data. Now they're stacking up tablets to 2/3 of the way to the moon. I don't know how they figure out how to do these things, but like what's the best analogy, but whatever. It's a lot of data, okay? There's a lot of data out there. So what the heck is going on? Where's all this data coming from? Well, from the internet, I guess. Okay, but really what do we mean? So, if I set all the people in the world typing at keyboards as fast as they can, we wouldn't generate that much data. Like Twitter actually isn't that much data. Okay, so you get everybody typing really fast. There's 4 billion people. It's just not going to generate that many bytes. All right, some, okay, decent amounts, but not that much. There's other stuff going on. One thing that's going on is there's lots of copies of the same stuff, basically movies. And when you measure internet bandwidth usage, it's for sure just, a small number of things being sent too many times to different people, right? So that's all about staging that data out and caching it and putting it in different places to reduce bandwidth usage. But storage-wise, a lot of the world's magnetic storage is being taken up with like copies of movies. Okay, so that's some of it, and that's actually not that interesting at some level, at least not today. It's not that much unique data. We don't do that much with it, but that's part of it. Okay, but what's really kind of interesting is what I call the industrial revolution of data. This is happening under our feet, where basically data is being stamped up by machines. Data used to be crafted by people typing at keyboards, or people making movies or making music, creating content. Okay, but now data is increasingly being generated by machines. Primarily these days, software logs, right? So all our software is spitting out logs about what's happening with it. That software is in the center of many of the systems of the world, commerce and government and so on. And so that just